Okay, let's get started. So I made an announcement. So this is basically what I'm planning on covering and doing throughout the rest of the semester. I have a faculty interview, so I will not be here the last Monday and the last Wednesday of class. And for that reason, I'm not having office hours on the last Tuesday. But I will be here on the last Thursday and the last Friday. So this week is completely normal. Next week is completely normal. Next week, I'm not here Monday through Wednesday, but I will be here Thursday and Friday. And then for that reason, we'll do a final exam review then. But are there any questions? Yeah. Okay.
When you're trying to initialize the vector 3 and 6, where you're trying to basically go 112,
Yeah.
11, I can't figure out how to do that one.
Okay, so for V3 and V6, let's just do V3. Actually, we'll do both. So let's just say n equals 12. Then the V3 vector will contain the numbers 1 through 12 without any repetition. Okay, so what is the order that V3 has elements? So what's the first one always? 1, and then in this case, next one is 12, and then what? 2, 11, 3, 10. Let's make this a little wider. 4, 9, 5, 8, and then what? 6 and 7. So, but any others? No, because we don't want a duplicate. So, if the number that we're looking for is n in general, not just 12, but n in general, what are the last two numbers that are entered? Well, what is 6 in relation to 12? Half. So the last two numbers that you add are what? N over 2 and n over 2 plus 1. But think about this for a moment. So this will actually really help you. Look at this pair. So 1 and 12. What do they add up to be? 13. What about these two? 13. Oh, do we see a pattern here? So let's think about this. So let's just say that we're going to add a pair like this, 1 and 12 or whatever. Let's just say that the number is n. The original number is n, and we're pushing back x. So x would be like 1 or 2 or whatever in this case. And n would be like 12 or the numbers that, the lengths of the vectors. What else do we need to push back also? Well, if this is n in general, what do the pair of numbers have to add up to be? If it's 1 and n, and then 2 n minus 1, what do the pairs add up to be? N plus 1. Oh, so if I'm pushing back x, some arbitrary value, what else do I have to push back? Well, the two numbers have to add up to n plus 1. So what do I have to add here? N plus 1 minus x. So because these two numbers have to add up to n plus 1. Well, think about this for a second. What is the range on what x starts out at and goes to? What is the lowest value that x will ever be? 1. And what is the highest value that x will ever be? N over 2. Including n over 2 or excluding? Including, right, because we have the 6th case over here. So how would you solve this? You would start a loop with a variable x starting at 1, go up to n over 2, add 1 every time, then you push back x, and you push back n plus 1 minus x in the same for loop. What about V6? So what are the contents of V6? 1, 1, Then what? Not 12. Because I have to have the same number of elements. It starts at, the next one is 6, yeah. Because we have a duplicate of every element. And then the next ones are what? 2, 2, 5, 5, and then 3, 3. And it's not Friday. I should have more participation. What is the next one? 4, 4. Thank you. Okay. So let's look at this now. So what did the terms add up to? The pairwise terms like this add up to be now? It's not 13 anymore. It's what in this case? Well, actually, you're technically right, but ignore the duplicate. 7, yeah. So so if the original number is, well, let's just say it's n. So let's just say we're pushing back x again. Well, what do we have to push back immediately after that? Well, if we're pushing a 1 right here, what immediately happens right after it? Another one. So I push back x twice. But then what do I push back next after it? Well, what did the two numbers have to add up to be? Well, not n in this case. It's n over 2 plus 1. So because it was n plus 1 before, but now because there's a duplicate everywhere, we only need to go to half of n. So n over 2 plus 1. So what do we have to push back next? They have to add up to n over 2 plus 1. So we have to push back n over 2 plus 1 minus x. Okay? Because ignoring the duplicate, these two numbers have to add up to n over 2 plus 1. But is that all we do? Of course not. What else do we do? If we push back 6, what do we push back next? The same thing, yeah. So we do that again. So in this, so before we had the x go up to and include n over 2. What should x go up to in this case? Well, what is the highest value that x ever goes to relative to n? N over 4. Which is why in the directions I made sure that the sizes of the vectors were always a multiple of 4. So that you can always divide by 4 with no issue here. So you just go to n over 4 inclusive, and then you just, for x, and you just push back x twice, and then n over 2 plus 1 minus x twice. Okay? Any questions about that? Okay. Oop, shit. All right. So let's see. So any questions on material otherwise? Okay. So what were we, wrong slides. What were we talking about so far? Pointer. So what is a pointer? It's an address, and what do we want it to do? So intuitively, what is it? Well, all it is really is just some integer. It holds some address, and it points to that address. That's all it really does. And we talked about a whole bunch of stuff, like arrays are really the same thing as pointers. We can do, we can look up the value from a pointer using the star operator called the dereference operator. I'm not sure why it's called dereference, because it's a pointer. It's not a reference, but because references are addresses, I guess that's the reason. We talked about different kinds of constant pointers, so whether we want to modify the data or modify the pointer itself or not depends on the scenario. Okay, so, and then we talked about next dynamic memory allocation. So when should we use dynamic memory allocation over just what we've been doing before? So when do we primarily use dynamic memory? Well, if we do not know how much memory we need at compile time, do I need dynamic memory? Yeah. So if I, for whatever reason, don't know how much data I'm going to need, then I need dynamic memory in some way. So like for vector, so if I'm going to be adding things to a vector, does the vector know at compile time how big the underlying array is going to be? No. So vector on the back end uses dynamic memory allocation. Luckily, we don't have to do that ourselves. The vector class handles it for us. Same thing with string. The strings that we deal with can be arbitrarily long. They're not just a fixed size. And so they use dynamic memory allocation too. So it's primarily when you don't know how many things you're going to need, how much memory you're going to need in advance. So like in this case right here, where we say some array pointer is equal to a new double 25. So how many doubles are in this array? There are 25. Do I know how big this array is going to be at compile time? Yes. So do I need dynamic memory in this case? No. So it's not required for when you don't need it, but if you don't know the size of how much memory you're going to need, you definitely need it. And so how do you actually create dynamic memory? You just say new. So new whatever, that'll create something dynamically created. So as an example, we did this before. So count right here is dynamically created because of the keyword new there. And array pointer is dynamically creating this array because also we're using the keyword new. But and it always returns to us a pointer. So that's one of the reasons why you should understand pointers, because dynamic memory requires that you use a pointer. So one of the issues that we saw was, well, if you wanted to free up the memory that you use back to the operating system, then you actually need to clean up the mess yourself. So #1 rule of kindergarten is what? What is #1 rule of kindergarten? Hopefully you remember. Yeah, clean up your mess, essentially. So if you create a mess using dynamic memory, you have to clean it up yourself. So hopefully you all abide by that. But anyway, let's just say that count and array pointer are dynamically created from here. So count is dynamically created as just a single integer, and array pointer is just some number of integers as an array. If it's just a single object, then we could just say delete that object name. If it's an array, then we have to say delete with square brackets the pointer for the array, the name of the array. You only use delete with dynamic memory because if you use something that's not dynamically created, when it goes out of scope, so it's like the variable's no longer usable, it automatically gets freed. So it frees the memory back to the operating system for you. You do not have to do it yourself, which is nice. But you may think, well, vector, as Ryan just said, uses dynamic memory, right? Because we don't know the size of the underlying array. But have we ever used delete a vector name at any point? It uses dynamic memory, but we don't use delete the thing. Anyone know why? That's the exact reason. So one of the really nice things about having an object wrapper around using dynamic memory, so like a vector holds the dynamically created object on the inside, but we're not exposed to that. One of the nice things about it is when the vector goes out of scope, it calls its destructor. Remember, destructor handles when we want to destroy the object. So destroying the object means releasing dynamic memory. And so we'll see an example of that. But so whenever the object goes out of scope, the destructor is called. And so in the destructor somewhere, there is a delete square bracket for the vector. And so whenever the object goes out of scope, it always calls the destructor. So let's just say that, let's ignore all that business. And let's just say I really like new and delete. I really want to create objects myself dynamically, and I want to delete them myself dynamically because I like managing my own mess. Sounded better in my head. Let's see. So what could happen? Well, we actually noted this last time. So if we have like some created object right here, let's just say we create a new array. So this has 25 integers. I didn't have to use dynamic memory here, but it just shows an example here. So let's just say that I'm a good person and I say delete array at the end. So is there anything wrong with this code at all? And it's not a trick question. Is there anything wrong with this? No. So I create the array dynamically and I delete it correspondingly. Everything's okay. But suppose that this happens. Suppose that we have some if statement somewhere, and let's just say this if statement is checking whether the user entered something invalid or not. And then if they did, we exit the main function. We quit the program. What's the problem now? It didn't get deleted. So no matter what the user does in this case, the array is always dynamically created, whether or not we return 0 at this point or not. So that means that if we do get into this if statement and there is no delete inside this if statement for this dynamically created array, then we just leaked memory because the program quits, but this array is still allocated in memory and can't be freed because it wasn't told, hey, this memory is now available because we didn't call delete on it. So what is a simple fix in this particular case? What could we do? Why not just say delete array here? Would this be okay? Yeah, so every single code path through the main function, no matter what happens, we have a delete right at the very end, and so everything is okay. Okay? So is there anything inherently wrong with doing this? No, there's nothing inherently wrong, but is this annoying? Yeah, so if we make this a lot more complicated, like it calls other functions which may or may not have the program stop, then we need to handle dynamic memory over there too. So this becomes very cumbersome to deal with, which is why vectors are so awesome. Because when the vector goes out of scope, then its destructor is called, which means it calls delete no matter what happens, which is awesome. Okay, so let's just talk about different types of pointers. So if we forget to call delete, so like in that example where we had the if statement and we quit the program, never saying delete, that's a dangling pointer. The pointer itself is dangling, not the memory contents, the pointer itself, because, oh, I have it backwards. Sorry, that's a memory leak. So a memory leak is when you do that bad thing where you have some memory and you never call delete on it. If you have dangling, a dangling pointer is when you have a pointer pointing to some dynamic memory. You call delete on the dynamically created memory itself, so like the array that we talked about before, but then the pointer now is not really pointing to anything you own anymore because you called delete on the memory. So let's look at the example from before. So here, let's just say that we didn't have this issue with the if statement and we just had this normal situation. Well, if I like tried to see out the pointer itself, just like print the pointer, that is a dangling pointer. Or if I wanted to print out the contents of the first index, whatever the contents are, that's a dangling pointer because we called delete here. So the recommendation is, well, don't use new and delete, but I'll get to you in a second. But if you are going to use new and delete, put the deletes right at the very end where there's no statements afterward. And then therefore we're okay. Yeah.
If you have an array that you put like data outside the bounds of the delete, also get rid of the data outside of the bounds of the array?
That is an excellent question. I am not sure. So the question is, so we have 25 integers in here. So let's just say that I called delete on elements that are outside the bounds of the array. I'm not sure, actually. I'd love to know the answer because that could be some security problems. So think about this scenario. So you have some dynamic memory here, or not. It doesn't even really matter. So if you call delete on some random address, which is some dynamic memory in a completely different program, then what possibly might happen is, well, if you call delete on this other piece of memory, does that piece of memory belong to that other program anymore? No, it belongs to the operating system now. So that means that if you try to access the contents inside there, you're now able to, because it doesn't belong to that particular program anymore. So, but I'm not sure if you can actually do that. Let's see. So I think in this case you have to, so remember, does C++ do bounds checking on the square bracket operator? No. So in fact, because we just have a pointer right here, it's not an array. Well, you can treat it as an array because the square bracket operator is just pointer arithmetic. So what you can do here is say delete array of 1. Well, this right here is just a pointer to a single integer, not multiple. So when I say this, I'm trying to delete other memory, not the integer that I'm holding. So I do not know what's going to happen. My computer might crash, but we'll see. Cannot delete expression of type int. Okay, so I think yeah. So I think this is built into the type system. So here it's recognizing that this is a plain old integer, but and so you can't delete something that is not the actual name of the integer itself. Whereas array of 1 was not the actual name, it's just some other integer, which is why it gave us a compile error there. But if we did 25 integers here, and then we tried to delete array of 100, let's see what happens. Okay, yeah. So I guess you have to delete the name of the location. But let's try this. So remember, we can do pointer arithmetic. So we can just say a different pointer is equal to array plus 100. So 100 places further, but it's still a pointer, and then we'll delete the pointer itself. Okay, yeah. So you really can do this, but there's this function called malloc, which is basically what new does. Yeah, so I guess what malloc does is it keeps track of what pieces of memory are allocated to which program. So there's like a little tag that says this chunk of memory is allocated to this running process. This chunk is for this process. And so when we tried to do this, it said, oh, what is the tag on that piece of memory? And it wasn't the current program. And so therefore it says, oh, you're trying to free up memory that doesn't belong to you. I'm going to try to abort now because you're doing something wrong. So maybe there is a way around this. I'm not sure, but it looks like it's pretty safeguarded here. But great question. Other questions? If you guys keep up asking great questions like this through the rest of your undergrad career, professors will love you. So you ask absolutely amazing questions. So thank you for that. Okay, so dangling pointer is when you call delete on the dynamic memory, but then try to access the pointer itself afterward because it's not pointing really to anything that you own anymore. A solution for this is setting the actual pointer itself to null pointer. So null putter, the thing that we talked about before. If you set the pointer to that, then if you try to dereference that pointer, the program will crash as you want it to, because you don't want to access something from a dangling pointer. A memory leak is when you don't call delete on a dynamic memory, as we've seen before. So I love the solution here that they propose. Free up dynamic memory after use. But as we saw, what is the problem with this? Or what's a potential issue? Yeah, we have to make sure we put delete every single place that could ever result in the program stopping. So, and if we add a new dynamic memory, then we have to put it a delete corresponding to it everywhere. So that's actually really difficult. So there's a way to get around that. And I can talk about that if you're curious. So you can return pointers. So you don't have to return things by reference or by value. You can return it by pointer. But this actually brings me to something that's kind of important. So let's just say that, ignore main for a moment. Let's just say we have a function f that returns a string. So I definitely picked string for a reason. Or vector, you can pick vector, but definitely not an integer. So let's just say we have a string s equal empty, and then we append user inputs here onto s. So I put this in a comment because it's not really relevant, but we're just putting stuff into the string s. We're making s longer and longer and longer, and then at some point we return s. So is there anything wrong with this code? Hint, it's not a trick question. No, there's nothing wrong with this code because we're creating a string right here and we're returning the string. No issue. But what might you think is a troublesome thing? So let's just say we have int main here and I call cout of f. Or maybe let's do it this way. So let's just say string result equals calling f and then I print result. Okay, so this is nothing really special here. We call the function f, we get the user inputs here, we return the string, it's a string, so then we return it here, assign it to this string over here in the main function, and print it. Nothing special. What appears to be an issue though, if this string is really, 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 really big? What could be a problem? Or looks like to be a problem, at least. Well, let's see. The string over here is going to be over here, but that means I have to, so I'm going to say a falsehood. This is not true, but what it looks like to be. Here's a string, and I'm going to copy it into this string, right? So I'm doing a copy of the string. What is one thing that we have talked about many times on how to avoid making copies? Pass by reference. Or maybe let's try returning by reference, because I don't want to make a copy. Is there anything wrong with this code? And in fact, there is. So let's understand why. So look at this variable s right here. What is its scope? Like where I can access this particular string. In both functions or in f? Just f. So when this goes away. So the s variable right here, we're returning it, but we're returning a reference, okay? So we're returning a reference to a variable. But what happens when a variable goes out of scope, as we just learned? The destructor is called. Mainly, it's freed up. There's nothing left in the object anymore. So I have a reference to something that doesn't exist anymore. You can see the problem now, right? Because the lifetime of this variable s is only inside this function. So when I look at result here, it's a reference to something that has just been destroyed. So it seems like we're stuck here. If I try to do this, it looks like a copy. If I do reference to try to avoid the copy, we have issues because we're returning something that has just been destroyed. So it turns out that this does not do a copy. So I invite you to actually look up why that actually is. So the reason why I said this is that there are technically 3 ways of returning from a function, which is just returning by value, returning by reference, and now returning by pointer. But which one should you try to avoid? Returning by reference, good. So, but that's actually not true either. So if you just have a normal function like this, just try to avoid returning by reference if you can. So return by value if you can, or return by pointer if you need to return dynamic memory. So if you have dynamic memory, because I'm just passing the pointer along, and the dynamic memory is not freed up when the variable goes out of scope, it's still there. I'm just passing the pointer along, and the memory is still there. So when we have dynamic memory, return by pointer is very okay. It's just when you have a non-pointer variable like this one, and you try to return by reference, there could be issues. So if you have dynamic memory, return by pointer if you can. You can pass by reference. That's no issue because the memory still exists from where you called the function. But returning has issues. So for memory leaks, if you create something via new, it has to have a corresponding delete somewhere. Yeah, so here is actually where, this is actually much more important than it may seem. So if you have a class like vector or string or whatever, if you're going to be using dynamic memory, allocate new inside the constructor because we're constructing the object. We need to create all the memory that we need, which makes sense to have dynamic memory there. So if you're going to be creating dynamic memory using new, put it in the constructor. And if you're going to be correspondingly deleting it, you need to delete it in the destructor. So the thing is, well, I actually never use this. So it's just only in certain cases do you actually need dynamic memory. Or if you do need it, you have it wrapped up in something. So like vector, for example, wraps up all the work for you. You do not have to manage it yourself. So, but sometimes you do. So if you need to wrap up new and delete, put new in the constructor, delete in the destructor. Any questions on memory leaks, dangling pointers, all that stuff? Mm-hmm.
So would it just be a really good rule of thumb to avoid passing by reference or using references in functions?
No, so passing by reference is okay because the memory is still in the original function. If we're trying to return by reference, it depends on what we're returning. So that's why I said it's a little bit of a lie. If it's a variable that you create inside the function and you return it by reference, that's a no-no. If you're returning something else that exists outside of the function, that's okay. And it's accessible by both functions, that's okay. Because it still exists outside of whatever the function is doing. So just try to avoid returning by reference. And in fact, there's another reason why you should return by reference, but it's a little complicated. It's actually basically just an optimization, but to avoid copies. But any other questions? Okay, so you can have pointers to really anything. So this isn't really unexpected here. You can have pointers to class objects. So if I have a student object, either dynamically created or not, I can just create a pointer to it, no problem. So it's exactly the same idea as with like integers or strings or whatever. You just set the pointer equal to the address of the thing that you want. Or you use new and you're all set. The issue is when you try to access attributes or functions of the underlying object. So remember, if you use the star operator, I'm looking up the value in the corresponding to the pointer. So if I do star pointer here, then I can just use dot like we have been doing before. So if I have a pointer to a vector, for example, then I can say star the vector name dot size, for example. And so I can look up the size of the vector that I'm pointing to that way. But if you want to avoid the star entirely, what you can do is use arrow. So yeah, so instead of doing star the pointer name dot member with the parentheses, which looks a little complicated, you can just use the pointer arrow the member and you're all set. And that does literally the same thing. It's just a shorthand. So I can set the student ID to be, if this is a public member variable, and this is a pointer, so then I say the pointer arrow the thing equals whatever value. Or I can call a function, the pointer arrow the function, and it behaves exactly as you would expect. Or you can use star the name of the thing dot whatever. Okay, so you can use dynamic memory for objects. So this isn't anything different. So instead of just saying new int here, you just say new whatever the object name is. So nothing new. And you use delete in exactly the same way. So nothing new. Let's see. So yeah, so how do we access the pointer member via the struct? So let's just say we have a, think of this as a class. So structs are the same as classes essentially. So let's just say we have a grade list pointer right here, and we're pointing it at some other grade list. Then if I want to access the grades pointer, then we have three ways essentially of accessing it. So if I want to access the pointer itself of the grades variable right here, which is the integer pointer inside the object, then I can just say the pointer arrow the pointer name, and then now I have access to the pointer, not the value, the pointer. Then another way we can do this is if we want to access the value that's pointed to by the grades variable right here, whatever this is pointing to, then we can use star test pointer arrow grades. Or you can use star test1 dot grades. So this is really for your information. I'm not going to test this because I never use this because I don't use pointers. But it's just, you may see this sometime. The vast majority of the time, though, you're just going to have a pointer arrow something. It's not going to be any more complicated than that. Okay, so the thing I really wanted to get to, which is smart pointers. So what are smart pointers? I briefly mentioned it last time. Yeah, so what were the issues with new and delete that we had? Yeah, memory leaks and dangling pointers, right. And there's something called double deletion. Don't really worry about that. It's just lots of problems with new and delete that you could deal with, but it's a lot harder to deal with than it needs to be. So a smart pointer is basically like vector or string, but for a single pointer only. Okay, so it's basically just a single object wrapper around a pointer, and that's it. So there are two types of smart pointers. So there are called what are unique pointers. And so what a unique pointer is saying that I have a resource right here, and I am the only person pointing to this resource. There's no one else pointing to this resource at all. So I'm the sole owner of that object. And the other type is a shared pointer. So what you might think that to be is I have a resource and any number of people can point to this resource. Okay? Those are the only two smart pointers. So we could have exactly one thing pointing to the object or any number. And so unique pointers, okay, well, I won't get into that, but shared pointers, we could add or remove corresponding people pointing at this object as the case may be. So if I have 3 people pointing at this object and for some reason I don't like the first one, I can just say, I'm going to free you up and have only the other 2 point to this object. Okay? Well, think about this situation. So let's just say we have a shared pointer and there's only one person pointing at this object. Is that okay? Yeah, so shared pointers can have any number of people. What if this single pointer pointing at this object, it says, I'm going to delete myself. So before, what would happen to this resource? If we just had new and delete, what would happen? So if we just have new and delete only, and we just have a single resource, and then there's only one person pointing here, and it says, I'm going to delete myself, but I'm not going to call delete on the object itself. What happens? We'll have a memory leak because the destructor on this resource wasn't called. That's where a smart pointer comes in. It says, well, for a shared pointer, what you do is you maintain a count as to how many people are pointing to this object. So we started off with 3 people pointing to this object, and then if one of them is freed, then this counter goes down to 2. And then if we go down to 1 person pointing to it, so the counter is 1, and we call delete, what happens to the counter? It goes to what value? What is 1 less than 1? 0. So if the counter ever becomes 0, then the destructor's called. So the shared pointers maintain their resource for you. You do not have to call new and delete at any point with a smart pointer, which is awesome. So let's talk about unique pointers. So a unique pointer is just a single owner of an object. And ownership can be transferred to another unique pointer. A unique pointer can't be shared, so I can't have multiple people pointing at this object, but I can move the ownership around. So if I have 2 pointers, one of them does own the object, and I move the ownership over, does the first one have ownership anymore? No, because I'm moving the ownership. Good. So memory for the object is deallocated when the unique pointer goes out of scope. So when the destructor of the unique pointer is called, then that resource is freed up. So it handles all the work for you. So how do you actually use this? So yeah, you need a different header called memory. And all you do is, so this kind of looks very similar to vector. So instead of vector of int, we say unique pointer of int. And then we put the name of the pointer here. And then, so you say, okay, Ryan, you said you didn't have to use new and delete anymore, but I see a new on that statement, right? So there's a way around it. But let's just say that this is okay. Then, so we have a unique pointer here. And then whenever the unique pointer goes out of scope, so like when, actually let's just do an example. So instead of just saying it. Let's actually do it. So let's have include memory here. So let's just say that we have a void function here. And then let's create a unique pointer of int uputter, and then let's call it and let's just put a new integer in there. So is the value inside the unique pointer dynamically created or something else? It's dynamically created because a unique pointer behaves like a normal pointer. So let's see. The good thing here is, what is the lifetime of this pointer? So when is the destructor going to be called for this pointer? At the end of the function f, right? So right here. So that means the destructor of unique pointer is going to be called, which means that the dynamically created integer on the back end will have the corresponding delete called, which is awesome. So you don't have to say delete at all. But the great thing about C++ in particular is we can override operators. So unique pointer overrides the star operator to say, I'm going to have this thing behave like a pointer. So I can say star uputter to access the value inside the pointer, exactly the same as a normal pointer. There's no difference there. In terms of this, there's no difference. The only difference is in the declaration. That's it. Nothing else is different. Yeah, so I can just say, I'm going to set the value inside of the pointer to be 5, and then I can print out the value inside the pointer. And as I said, we can't share ownership of a unique pointer. So then if we want to change ownership from one object to another, we have this special function called move. I'll talk about move in a later lecture at some point. But you can think of move as I'm moving the ownership of uputter to the other unique pointer. So after this move statement here, unique pointer does not have ownership of the object anymore. And the second unique pointer does have ownership of the object. So we're moving ownership over. The function doesn't really do this, but it's a good way to think about it. But any questions? Yeah.
Transfer ownership to a shared pointer?
So can I transfer ownership of a, yes, yeah. So you can transfer ownership from a unique pointer to a shared pointer, but not necessarily the other way. Because if the shared pointer has two things pointing to the object, then if I create a unique pointer, then the unique pointer says, I'm the only thing pointing to this object. And so I can't have a different thing pointing to this same object. So you can transfer, I think, from a unique pointer to a shared, but not the other way. Other questions? Okay, so here's actually the way you get around saying the new statement. So I said here, well, you do have to say new here. For a long time, that was the way to do it, but there's actually a better way with a special function called makeUnique. So here, you do not have to say new at all. So you could completely avoid new and delete entirely if you just say makeUnique. But the issue is you have to use C++ 14 to get this feature. So this is one of the reasons why I had you do the written assignment, because this is a recent version of C++, like 5 years ago or something, relatively new. And so if you're on top of what everyone in a C++ community is doing, then you can be aware of these awesome features that come in later versions of C++. So I'll stop there, and I'll see you on Friday.